recording has started. 4.5, our last piece of our graphing unit. This one does have some practice odd problems, which you might want to do if you're working on these even problems, this trig homework. I'm not sure what day that's going to be due. I feel like there's a piece got chopped off there. Oh, it did. Look, A and B. I fixed that for next year in case you want to fail and come back next year and see it corrected. So that there, B is there, part A and B. This trig homework probably gonna be due on Friday, probably. Okay, so I might just go ahead and write that down. Where is the pen that I am wanting to use? I'll use this one. So, due Friday, 3/21. Okay, so here's the deal, Lucille. If you're struggling with one of these even problems, there's probably an odd problem kind of like it that you could do and check your answer in the back of the book to see if you're on the right track. Okay? Now, what we're dealing with is simple harmonic motion. We are going to be looking at real world situations that form sine waves or cosine waves. All right? So, one of the first situations that we look at is shown in this picture. If you look at this picture, do you have any idea what is happening in that picture? A lot of stuff is happening there. What this is, let's read about this one, okay? It describes the motion of a point or an object that either vibrates. Okay, so what does vibrate mean? Oscillates. Do you know what oscillate means? It's not real different from vibrate. Like you might have an oscillating fan, or you may say like a pendulum swings and oscillates, so it just goes back and forth regularly. Or rotates, okay? Or is moved by wave motion. Like what? Sound waves, okay? All of these things, if you track them over time, the movement of just one point over time, it's going to form either a sine wave or a cosine wave. You really, how do you know which one, if it's a sine or a cosine wave?
If it's dipping.
It's both. All sine waves can be written as cosine waves if you throw in a phase shift, huh? So, they are called sinusoidal waves, which is just a fun word to say. So, anyway, a traditional example is a mass, okay? So look, right here, this is my mass. Let's pretend I have this, lead ball or something, a weight of some sort. In this picture, it's round, okay? A mass attached to the end of a spring. Okay? Now, right now, see how my spring is coiled? Maybe I have that mass lifted up to what is called the equilibrium position. If I let that go, maybe I'm holding it in position with my hand, if I let it go, what's going to start happening? Go down, and then what's going to happen? Go back up and down and up. Now, will that work infinitely? Why not?
Because it doesn't have the same energy.
Okay, so what's going to happen?
It's going to stop or something.
Stop eventually. Why? What's causing it to stop?
Inefficient energy transfer.
Oh, that sounds pretty good. What's causing it to stop here on Earth?
Gravity.
Eventually, gravity is going to slow it down. Okay, so if you could have perpetual motion, you'd be good. Some cases, you may have a motor rotating the object, so as long as the motor's going, that object's going to go over and over and over. All right. So anyway, in this picture, our object seems to be going up first and then down, but I'm thinking if I had a spring, I might have it in the highest position and let it go, and then it starts coming up and down. It would look like kind of a cosine wave. This one looks like a sine wave. I don't think the sine wave's a great, you know, what gets the spring going up first.
Maybe they just had it here and threw it.
They just went, "Pwah," and then they let it go, right? Okay, I can think of a situation where we stopped the lecture and pledge allegiance.
I
That's
pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Now the Texas pledge. Honor the Texas flag. I pledge allegiance to thee, Texas, one state, under God, one and indivisible. Now please remain standing for a moment of silence. You may be seated. We do not cross doors open on campus for any reason ever. If you see a door propped open, please close the door for our safety. Teachers, please check for dress code. If there are any issues, please send the students to the office.
memo that we were supposed to wear gray pants and black.
Early college students need to turn in your dual credit applications to the office by this Friday. We would like to congratulate both our Pirates baseball and softball teams on their huge win against West Holden last night. Today's down for the day.
Let's take
Write
a
on
picture
extra
together.
notes because they
Got
might
your dark
not
hair
know.
going and everything.
Today's Bible verse. Philippians 4:13, I can do all things through Christ who strengthens me. Today is corn dog day and poultry day. Thank you. Have a great day.
All right, so anyway, let's fill out this little blank before I tell you the situation that I can think of that might mirror this. What kind of wave do you think of when you see this? Sin?
I was going for seeing.
Sine wave, perhaps? Okay, first of all, let's make sure we understand what is meant by equilibrium position. So it's the position when an object is at, any idea? At rest. Okay? That's your equilibrium position. But it's in our graphs, that will be your horizontal axis. Okay? So the equilibrium position here is actually halfway between your high point and your low point. And I think on some of your work yesterday, you had graphs and you were trying to figure out, oh, what's the equation of the graph? Well, to find your axis, if it shifted, you had to look, what's halfway between the highest and the lowest point? Let me draw that axis. So what you were drawing was, in these applications, the equilibrium position. So here is an example of harmonic motion. I will draw it to the best of my ability, that we could come up with a story that actually had it starting at the rest position and then taking off and going up. Think of, well, first I'm going to draw my picture and see if you can even guess what I'm drawing. Any guesses yet?
Sir.
You might think so, but that's just the beginning of it. You know what I'm trying to draw here? A Ferris wheel. It is a Ferris wheel. So let's say that you got upon the Ferris wheel, and you know, when you get in your little, you know what they call the little carts in a Ferris wheel?
I don't get on.
A gondola. I'm kind of with you there. I'm not real big on being way up high in the air. It kind of freaks me out. So I'm usually down on the ground taking pictures of everybody that's on the Ferris wheel. I don't like it. And I sure don't do things that have me doing this, because then I just get sick. Anyway, you know, you load up at the bottom, and then they move you, and they move you, and they move you, they move you, move you, you know, whatever. Let's say that you ended up right here in this little cart. You're kind of halfway between the highest point and the lowest point, aren't you? And so that's when they say, okay, we're all loaded up, pull the lever, start it going, and your point starts going that way. Well, if you graph that over time, well, I just drew it solid, okay? But let's say that's the center point or the axis, and you started going up. What's going to happen? What's your motion going to look like over time? Uppity, 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 down. Now you're on the other side, right? Now, here you're going around, but if I'm tracking that on an XY axis, your motion over time creates a sine wave. Agreed? Okay? So, simple harmonic motion. We have two basic functions that symbolize this. Well, you know, if I told you to give me an equation of this, what kind of would your equation look like? Y equals what?
Sine.
Okay. Sine of x, right? And what if I wanted to change your period? What would I put into an equation to change your period? What letter affects the period?
B.
Where would the b go?
After sine.
Okay, sine bx, right? Well, check out these two equations that we're going to be dealing with. Tell me how that is either similar or not similar to what we have looked at so far. There's a W, but is it a W?
It's an omega.
It's a omega. Aha. Okay. This has omega in it. What does omega talking about?
It serves as the
Okay, well, hang on. Angular speed, right? Okay. So omega serves as our B value. It works like our B value. We can use the omega to figure out our period. All right? So we are just going to be putting in, when we're dealing with a simple harmonic motion in real life applications, omega is the variable we use for our B value. All right? Works just like B. All right? What's the A for? Amplitude. Amplitude, what do you think goes on my blanks? The distance from the equilibrium, which is another word for our axis, right? To the blank or blank point. Highest or lowest point. I don't like the feel of that pen, but that's okay. I found the one I do like, sitting right here. All right, if I need to find my period, I'll do 2 pi. Why 2 pi?
because it's one full rotation.
And 1 full rotation, okay? Perfect. And so that's 1 full period in sine or cosine waves, right? So our period will be 2 pi divided by our omega. Or if I have the graph and I need to create the equation and I need the omega, it's 2 pi divided by the period on the graph. And again, they keep mentioning where our B value or our omega is greater than 0. We just have not dealt with having negative B values, and we're not, so there. Okay? Now, a refresher from yesterday, because you had to remember something about frequency on that major grade yesterday. What do you need to remember about frequency? It's the reciprocal of the period. So if you need to know the frequency, find the period and get the reciprocal, right? When you are giving a frequency, it's going to be either cycles per time unit, so it might be 8 cycles per minute. But there are several other words that will be used that mean the same thing as cycles. So, what are some other words instead of cycle? We named some a little while ago. Why don't you look up at the top? Huh? Rotations. It could be rotations. What's another word that we seem to almost interchange with rotate? Rotations. It means turn around in a circle.
Yeah. It's another R.
revolutions. Okay, we might also see oscillations. You might even see periods. So, cycles or rotations or revolutions or oscillations or periods per time unit. When you give me a frequency, make sure you're saying revs per minute or RPMs. What's RPMs?
Rotation. Or
Revolutions per minute usually. Okay? So it might be by the hour. It might take a year for something to happen. That's going very slowly. Okay? So, with that in mind, let's work some problems. Primarily, we will either be using S of t. Remember, S is the variable that physics likes to use for position. S of t. Why t for the variable? Over time. All right? So it'll be a cosine omega t or maybe sine. How are you going to know whether to use the sine version or the cosine version of the equation? Depends on where your object starts. So if it's starting at the highest position and you let it go, especially if it's a spring, it starts high and goes low. If it starts at the lowest position, so which would you use if you're starting high and going low?
that would be cosine.
Cosine. What if you're starting low? What if you took your spring and you stretched it as low as you could go and you let it go? Boing.
Oh wait.
That would be negative cosine, wouldn't it? Yeah?
Oh wait, negative cosine. Okay, I was about to
Okay.
say. I thought you were gonna
But-
say sine. I was like, wouldn't that be a rest?
So what if you were at the very middle of the Ferris wheel and you start, oh, by the way, if I click this, I don't have to have all that extra junk in the middle of my picture. Don't know why, I keep forgetting that. So if it somehow starts at the rest position, you would use a
Sine.
sine wave. Okay, so let's look at some examples from the book. So, example 2 from the book. Suppose that a weight on a spring has initial position S sub 0 and period P. Okay? Now, I said S sub 0 because a lot of times sub 0 is used for initial, but what does that actually say? It doesn't say S sub 0. What does that say? S of 0. That's an ordered pair. So this, when you have 0, this is your y-intercept. Or, in other words, it's your beginning point, isn't it? So if you were to look at this problem and it says S of 0 equals 5, what's that telling you? Okay, that means if you were to draw this graph, and in a second I'm going to kind of want to see this graph. If you were drawing this graph and you're starting at 5, it means you're starting at the high position. So what kind of formula do you think I'm going to want to use? Cosine. Which they actually told me anyway. Use cosine. Okay? So we're using cosine. Notice there's no place here for a phase shift. So if I'm giving you S of 0, I am giving you the y-intercept. There's no phase shift, so that has to be my highest point. Okay? So we are given S of 0 of 5, and we are given P of 1.5 seconds. So what does that tell me? What's that P equals 1.5 seconds telling me?
How long is it?
To do the whole valley, right? So if I'm graphing this, I'm graphing a cosine wave that will complete a cycle in 1.5 seconds. So my x-axis is counting seconds. And my y-axis is counting what?
Inches.
Ah, but what is it? Inches. I heard inches, right? So it's the height in inches. S in inches. Because it's really my S axis, because they didn't call it the Y axis, right? And this is my T axis, which is being measured in seconds. All right? So, before you fall asleep on me, Lane, you are so with me, right? We have to write this function. Can you help me write this function? Or in other words, give me the equation for the movement of this weight on the spring. So by the way, you guys, we are in a mathematics class, so we are not considering the dampening of the wave over time because of gravity or whatever else. If you're curious about that, I think there's some information about that in this chapter in the book. But we're going to assume like we're in a vacuum and there's no gravity and there's no drag, there's nothing, and we just have perpetual motion here. Perfect. Yeah, this is what you do in a math class. You assume the perfect situation. You know, calculus assumes more of what happens when these other things throw in. But perfect situation, perpetual motion, this is going on forever and ever and ever. So, tell me, Lane, how am I going to set up this equation? What am I going to use for my A?
Your A, okay.
What am I going to use for A?
5.
Okay, 5. So, the A equals 5 because our beginning point was 5. Because there's no phase shifts, so that means we're starting up high. Alrighty? So, then what else goes in my equation?
Cosine.
Cosine of, and I need the omega, but they didn't give me the omega. It's like a B value, right? How do we find that? 2 pi divided by, I don't really want to divide by a decimal, okay? So what could I do with this 1.5? 3 halves. And then I go, oh, I have a complex fraction, and how do I divide by a fraction? Flip it, reciprocal it, or whatever your word is. Reciprocal it. And multiply into what is our omega? 4 pi over 3. Do y'all agree with that? So where does that go in my equation?
After the cosine.
4 pi over 3. Is that the complete equation? No, we need another variable. Finish it off with
3 over 2. It's probably the easiest. Wait, am I wrong?
There's my omega. What comes next?
T.
T. There's my equation. Y'all were trying to make that harder than it was.
Yeah, I didn't know we were splitting it.
Yeah, that's it. That's it. That's how we get that function. Okay? So, now, evaluate S of 1. So what would happen if I plugged a 1 in here? Okay.
T at the end in the first equation.
Okay, yeah, so I'm going to plug that in for the T, right? So what's it going to look like if I plug a 1 in right there? It's going to not change it, is it? So my equation is going to say S of 1, or in other words, S is my position at 1, by the way, at 1 what? What time units are we using here? So my position after 1 second is going to be 5 times the cosine of 4 pi over 3. And I might plug in a 1, but seriously, that's just for me showing I plugged a 1 in right here. Just so in case you have to plug in a 2, you could see that. Well, y'all, clean that up. What do we have? It's 5 times Do we know the cosine of 4 pi over 3? Is that a unit circle thing? On a unit circle, where does 4 pi over 3 fall? Which quadrant?
Third.
Third quadrant. Is it close to the x-axis or far away from the x-axis?
Far away.
Your thirds are far away. So what's the cosine of that?
So bottom is 270. That's like 240 or something.
Not in degrees. Stick with radians here.
Negative.
Okay? Yeah, and honestly, it's not degrees because we just
Yeah.
plugged in a radian. We are
Yeah.
looking for a move, and so we went to the left. How far?
Square root of 2.
No, that's your y move.
Line.
Your x move was left 1/2. If I needed the y move, then I would have had the negative square root of 3 over 2. But you were correct, Felipe, it's negative 1/2. Y'all, that's kind of a pretty number, right? What happens if I multiply 5 times a negative 1/2? Negative 2.5. So I could figure out, I could put this point on this graph, right? Where would I put it? Where would 1 be? Okay, 1 whole period is 1.5, right? What's half of 1.5? What's this low points? What's half of 1.5? 0.75. Where would 1 whole be?
It's like your quarter point.
Somewhere, it's not really the quarter point. It's a little bit before it. This is about where the 1 would be. So if I graph that, it says it would be at negative 2.5. Did my drawing kind of match that a little bit? Okay. It wasn't the best cosine wave. There certainly was no grid involved. But would you be confident that you're on this side, on the right side of that valley, not on the left side? Not at the lowest point, not at the highest point? Okay? So, with that in mind, this was a two-part question. First of all, it said evaluate S of 1. Well, S of 1 is negative 2.5, and let's say what we're talking about. Negative 2.5 what? Is it an X value? It was I plugged in the X value, and it gave me a Y value or a height of my position. So what's my position? Negative 2.5. What am I measuring? Inches. So I am 2.5 inches below the equilibrium point. But that's only half of it. Don't turn the page. Is the weight, because remember this was a weight on a spring, is the weight at that point of time, 1 second, is it moving downward or upward?
Upward.
How do you know?
Because it's on the climb.
It's on the climb side. So that weight was going down, 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 down until it met the lower limit. And then it started climbing, so it was going upward. I am pretty sure that you have a question like number 2 in your trig homework. I think it's your number 4 question. Very similar. Okay? Turn the page. Let's discover some other fun stuff. Okay. A note on the piano has a given frequency of F. So, how do you get different sounds out of a piano? How does a piano even work?
A little hammer hits chords.
A little hammer hits these metal chords, right? All right. What makes the different sounds?
The tightness.
The tightness? It's not the tightness. It's
Or is
really
it
the
the
thickness causes it to vibrate either slower or more quickly. And the higher the frequency, the higher the sound. The slower the frequency, it vibrates lower, slower. All right? So, anyway, a particular note on the piano has a frequency given by F. And they give me an equation. Oh, okay, there's a typo here. I thought I had fixed every one of these last year, but I didn't. There is a formula given to you, but do you see how yours says cosine, cosine? When I transferred all of my notes from Little Cypress that were done in Microsoft Word over here and rolled them into a Google Doc, everywhere that I had cosine, it put a cosine in front of the cosine, and a sine in front of the sine, and a tangent in front of the tangent. And this was a serious, big issue in Trig because I had to go back and delete a whole lot of double sines and double cosines and double tangents. I thought I got them all until yesterday. I was like, I missed one. So it's fixed for next year if you'd like to fail and come back. But right now, it's not the cosine of omega t. Just get rid of one of the cosines, okay? All right, so does this look familiar now that you've gotten rid of the double cosine in it? It's that same simple harmonic motion parent, isn't it? All right, so suppose the maximum displacement at the center, so as it vibrates, it's being displaced from its rest position, isn't it? You don't hit the piano key, the cord or the wire doesn't vibrate, right? You hit it, doing, it starts vibrating. Okay? The maximum displacement of the piano wire is going to give S of 0. So they're giving us a cosine wave because at 0, it's as maxed out as it can be. On our graph, that means it's at the top of the valley. Make sense? All right. So find constants A and omega so that the equation S of t equals A cosine omega t, and it models the displacement. So what they're asking is, one, you need to create S of t from the given information. Then they're going to have us graph it in our calculator, which we will deal with in just a moment. But let's get the equation first. So the information they give me is the frequency, and then they also give me S of 0. What do I need to fill out this equation? Okay. How am I going to get the period?
We do the reciprocal.
So the period is going to be the reciprocal of the frequency. So a week or so ago when I said you need to remember this, this is twice in 2 days that you needed to remember that, huh? Okay. So what is my period then?
1/100.
Okay. My period is it's not 1 over what?
110.
110. Good. So I just put that right into this equation, right?
No,
No, I don't. Why
you
not?
gotta do the 2 pi.
I need to turn it into omega, which is 2 pi times the reciprocal of the period. So you really could say omega is 2 pi times your frequency if you happen to know your frequency, right? Okay, so I use that, get the recip again, to multiply that times my 2 pi, and now tell me about my omega.
Pi over 55.
Did you flip this back over?
Nope.
So if you feel like you're double flipping, you could just remember omega is equal to 2 pi times the frequency. So what do you come up with? Give me a different answer.
220 pi.
220 pi. Okay. Do I have my A value? If it's a cosine,
11.
your A value will be where you are at 0. Okay? So, let's write the equation. What's S of t equal to?
0.11
Mm-hmm.
cosine
Of
220 pi.
t. There is your equation. Now, it wants you to graph it in the calculator, and it gives you the window to use. So grab your calculator, turn it on, and do you know, okay, let's go first to y equals. This is where we put in functions so we can see the graph. Have we even graphed with the graphing calculator since you've been here? Okay, so we're going to type this in. 0.11 cosine, and what is the argument that goes inside the parentheses? It's actually this whole thing. So 220, where's the pi symbol? Okay, pi symbol is right above this little up arrow in blue, second pi. And our variable is t, but if you are putting a function into y equals, we always use the x as the variable. The calculator doesn't want a t, it wants an x. Now, one thing very quickly, this is in radians, and we need to check to make sure our calculator is in radians. How do I check if my calculator is in radians? Mode. I'm in radians. How about you guys? Okay. Then, I can go back to look at my function. I want to see the graph. Now, I'm going to go ahead and show you the graph, but then they gave us a certain window. If I hit graph, the calculator, I mean, if you look at it, it's a very tiny little sine wave, right? But your calculator defaults to this. Take a look up here. Your calculator defaults the window from -10 to +10 on the x-axis, -10 to +10 on the y-axis. They want me to change that viewing window, and to do it, the window button is right next to the y equals. So, they want this is my x domain, and this is my y values in that second one over here. So, for my x minimum, we're not going from -10 to +10. What are we going from? 0 to, yeah, 0.05. All right, not nearly as much, right? Remember, this has a period or a frequency in, what are we measuring in? Is this in seconds? Does it say something like that anywhere for us? Okay. It doesn't say it, but I don't think it's minutes. Okay. It may, I don't know. I think it's vibrating 110 times in a minute or 110 times in a second.
No, it would be more in a minute.
I think, yeah.
It'd be in the thousands, I think.
Okay, so pretty sure we're talking seconds here? They didn't tell me. How rude. And, you know, if you heard me play the piano, you would realize I just don't understand piano well at all. Okay, so we're looking at how many oscillations will we see in 5/100ths of a time unit, which we think is seconds. But we also are changing our y values, because you saw the y values, you weren't seeing very much, were you? You know, because your amplitude is, excuse me, 0.11. So they change our y values to what?
-0.3.
And 0.3. So we should be able to see 0.11 pretty nicely if we're going only to 0.33, right? So now, if you hit graph, you've adjusted the window so you get a really nice picture, don't you? All right, now you need to listen to me, but you can't until I get some water, because I'm coughing. Every time I see you two, it cracks me up. This is so cute. It's like you're in a school where you have to wear a uniform. Okay, so listen to me. You are doing one like this on your trig homework. I want to see the graph. So here's what you are going to need to draw for me. All right? So what are my high points and low points located? What numbers are going to be my top and bottom? Which I might want to give myself some little guide lines for up the max and minimum value, which are not spaced really evenly. But what are the numbers with these? I'm going to be drawing my cosine wave going up and down between these two levels. What is that highest point? Look at your A value. 0.11. What's that lowest point? Negative 0.11. Okay? Now, I am not going to ask you for anything along your x-axis. What I need you to do, and you need to do this correctly because when I'm grading it, I'm going to be counting in this window, which just went to sleep on me, how many complete cosine waves do I get? 1, 2, 3, 4, 5, and so you need to draw. So I think I'm just going to give myself 1, 2, 3, 4, 5. I'll put low points halfway in between them. And I got to make sure I end low, right? So you have to count them. I will be counting your peaks. All right? So 1 period, 2 periods, 3 periods, 4 periods, 5 periods, half a period. And that is part of what your answer needs to look like. Okay? So, can you do that? What if you do not have one of these graphing calculators when you do your homework?
Calculate 84.
Huh?
Calculate 84.
What, do you have an iPhone or a non?
iPhone.
iPhone, there's an app called Calculate 84. Okay?
Just don't, well, my phone doesn't, and now it's wanting me to pay to like use the graphing part of it.
Yeah, that happened to my, I had a phone app for a while that gave me everything and then it stopped giving me everything. But you could also, do they have any of these calculators down in the library?
No,
I don't think so.
All right,
but you
Okay.
can just find one.
You know, there's a website called Desmos that you
that's the
can
green one.
work with that one too.
It's the SAT one.
Yeah.
Gotcha. All right, we will start here tomorrow. Goodbye, teenagers.
But
Goodbye. Oh, I should probably stop this video.